Here we have shown the open belt drive. Now as shown over here, this is the center distance between the two pulleys. This is known as the driver pulley and this is the driven pulley. Now R1 is the radius of the driver pulley and R2 is the radius of the driven pulley. In this particular case, when this particular pulley, driver pulley, rotates in clockwise direction, the driven pulley also rotates in the clockwise direction. Now the power is transmitted from this driver pulley to the driven pulley due to the firm frictional grip between the belt and the pulley. So as you can see over here, this is G, J and E. This is known as the angle of lap on the larger pulley, whereas this E, K and H, this is known as the angle of lap or angle of contact on this particular smaller pulley. So this is the arc for which the belt remains in contact with the pulley. Now as you can see over here, in this particular case, this is theta, that is known as the angle of contact, and that will be equal to pi plus the alpha which is present on this side plus alpha that is present on this side. So it is pi plus 2 alpha, that will be the angle of contact or angle of lap on the larger pulley. Similarly, on this particular pulley, that is smaller pulley, the angle of lap is 180 minus this particular alpha and this alpha, so it is pi minus 2 alpha or 180 minus 2 alpha. So that we have written over here. So in case of this larger pulley, the angle of lap is given by 180 plus 2 alpha, and we have converted that value into radian. Similarly, in case of the smaller pulley also, the angle is 180 minus 2 alpha into pi by 180 radian. Now from this particular side, the belt is pulled and it is released at the top over here, and therefore this side is known as the tight side, whereas this side is known as the slack side. So what we can say over here is that as the belt is pulled on this side, it is in tension, whereas it is released on this side, so it is in compression. So there is alternate tension and compression that is produced in the belt drive, and that phenomenon is known as the slack. That phenomenon is known as the creep in the belt drive. Now as this particular radius is R1 and this radius is R2, if we draw a perpendicular, so this is the perpendicular that we have drawn, so O2M is perpendicular and it is perpendicular to this particular O1E, or it is parallel to this EF as you can see over here. Therefore this distance will be nothing but R1 minus R2. So we can define this small angle, geometric angle alpha over here. So by geometry, if this angle is alpha, this is also alpha. So this alpha, sine alpha, will be equal to this opposite side. So this will be R1 minus R2, because from O1 to E, that distance is what we can say R1, whereas from M to E, this distance is nothing but R2, and therefore this O1M distance is R1 minus R2. So we can say that sine alpha is equal to opposite side, that is R1 minus R2 divided by this hypotenuse, that is nothing but the center distance x. So that we have written over here. So sine alpha is given by R1 minus R2 divided by x in case of the open belt drive. Now let us try to derive to understand how to derive the equation of this ratio of tension, that is T1 and T2, that is the tight side tension and slack side tension. So for that we have taken into consideration the small arc on this particular pulley. So we have taken into consideration the smaller pulley, and a small arc is considered over here, that is PQ. It is making an angle of delta theta at the center. So if this angle, total angle is delta theta, this angle will be delta theta by 2. If this angle is delta theta by 2, then this particular angle is delta theta by 2. Now as it is tangential, so this angle is 90, so 90 minus delta theta by 2 will be this particular angle, and again this particular one, this is vertical, so this vertical is making angle of 90 degree with the horizontal, so 90 minus this 90 minus delta theta by 2, so that angle will be delta theta by 2. So we can say that if this angle is delta theta by 2, then this particular angle is also delta theta by 2. Now let us see the various forces which are acting on this particular small element PQ. Now in this case, the normal reaction is considered, which is perpendicular to the surface. So even though it is a small arc, we are considering it as a vertical surface, and the normal reaction will be perpendicular to that particular surface. If the rotation is in the clockwise direction, then frictional force is mu into Rn, which will be acting in the opposite direction. Then as this is the tight side, we have considered a small element PQ, and at point Q the tension will be slightly larger than the tension on the slack side, so it is T plus delta T. So we can say that if T is the tension on the slack side, then T plus delta T will be the tension on the tight side. Now this T plus delta T is making an angle of delta theta by 2, and that we have already seen. So it will have two components, the adjacent component is cos component and this opposite component is sine component. Similarly, in this particular case also, this T will have adjacent component as cos component and this opposite component is the sine component. So we can say that this small element PQ is under equilibrium under the action of all these particular forces, that is normal reaction Rn, then T plus delta T cos delta theta by 2, T plus delta T sine delta theta by 2, mu Rn, T cos delta theta by 2 and T sine delta theta by 2. So for the equilibrium of this small element PQ, we can resolve these forces horizontally as well as vertically, and applying the conditions of equilibrium, we can derive the equation for ratio of tension in this particular open belt drive. So if you apply the conditions of equilibrium, then we can obtain this particular term. So summation of Fx is equal to 0. If you consider forces towards right as positive, then Rn will be positive, that we have indicated over here. This T sine delta theta by 2 is in the negative x direction. Similarly, T plus delta T sine delta theta by 2, that is also in the negative direction. So those are negative, and that is equal to 0. Similarly, we can apply the conditions in y direction also. So summation of Fy is equal to 0. So upward forces, they are considered as positive. So this is considered as positive. So mu Rn is positive, T cos delta theta by 2 is positive, and this is acting in the downward direction. So that is negative. So T plus delta T cos delta theta by 2 is equal to, that value is negative, and that is equal to 0. So using these two conditions, we can derive the equation for ratio of tensions. So let us start with the first part, that is resolving horizontally. So as we have already seen, Rn is positive, T sine delta theta by 2 is negative, and T plus delta T sine delta theta by 2, that is also in the negative x direction. So therefore Rn will be equal to Rn minus T sine delta theta by 2 minus multiply by this sine delta theta by 2 inside the bracket. So it is T sine delta theta by 2 minus delta T sine delta theta by 2. Now for small values of delta theta, sine delta theta by 2 is approximately equal to delta theta by 2. So in this particular case, we have substituted delta theta by 2. So wherever we are having sine delta theta by 2, we have substituted delta theta by 2 for this. So this is Rn is equal to T delta theta by 2. Transfer these negative terms on the other side. Now delta T delta theta by 2, it is very small, so that is neglected. So it is only T delta theta by 2 plus T delta theta by 2, that is 2T delta theta by 2. So cancel out these two. So therefore normal reaction Rn will be given by T into delta theta. So let us call this as equation 1. Now resolve vertically. Upward forces are considered positive and downward forces are negative. So T cos delta theta by 2 is positive. F is equal to mu Rn, that is also positive. Whereas T plus delta T cos delta theta by 2 is negative. So minus T cos delta theta by 2 minus delta T cos delta theta by 2. Now for smaller values of delta theta by 2, cos delta theta by 2 is 1. So in place of cos delta theta by 2, substitute 1 in the above equation. Now cancel out this T. So therefore we can say that mu Rn minus delta T is equal to 0. Or mu Rn is equal to delta T. Now from equation 1 we have already seen that Rn is equal to P delta theta. So substitute that value and separate the variables. So mu delta theta is equal to delta T upon T. Now integrate this from 0 to theta is equal to 0 to theta is equal to theta, where theta is the angle of lap or angle of contact and tension is slack side tension to tight side tension, delta T upon T. Now integration of delta theta is theta and the limits are from 0 to theta. Integration of 1 upon T is log T to the base E and the limits are from T2 to T1. Substitute the upper limit in place of theta minus the lower limit. Similarly over here in place of T, substitute the upper limit, that is T1, minus in place of T substitute the lower limit, that is T2 to the base E. So this is nothing but mu theta is equal to log m minus log n is log m upon n. So this is log of T1 upon T2 to the base E. So using the definition of the logarithm, we can say that this is nothing but e raised to mu theta is equal to T1 upon T2. So this is the expression for ratio of tight side tension to the slack side tension in case of the flat belt drive.